So previously we have seen that if you have a morphism of schemes and f is a sheaf on the domain, then we can push forward and get a sheaf on Y. And nicely in the last video, if f is quasi-coherent and this morphism small f is a closed subscheme, then actually f push forward of f is also quasi-coherent. Now, we would also like to have a way to go back. So if you have f, for example, a quasi-coherent sheaf on Y, can you get the pullback being a sheaf on X? And the construction for this is as follows. So we have this data, and then assume for the beginning that we have X and Y being affine. Then we know that F, this morphism, comes from a ring homomorphism in the other direction from S to R. And since this curly F is quasi-coherent, we know it comes from S module M. So this is the input data. And now to define what the pullback is, we would like to come up with ideally an R module, which should have something to do with this M. And the idea there is we can use the tensor product. So we note that the M and the R are S modules, right? One's from this map and one's by assumption. And so we can take the tensor product over S. And this is not only an S module, but in fact, it's also an R module. Because now if you want to multiply by an element in R, you can just multiply in the second coordinate. This is the standard trick to get a new module over a new ring, just tensor with this ring. And then we get a sheaf by just taking the tilde over it. And this is now a sheaf on X because we had an R module and X is spec R. And we can just say, well, we define the pullback of F, curly F under the map F to be this sheaf. So this is pretty hands-on, and we understand very well what it does on the module level. But we also want to have a construction which works for arbitrary X and Y. And here the problem is that this easy definition of the push forward does no longer work. The problem is we need to say on an open set U of X, what are the sections of this pullback? And the problem is this open set might map to something which is no longer open. Can be pretty bad inside Y. And then we can't really take F on this image. Doesn't make sense. We can only evaluate this sheaf on open sets. And so the idea here is we will go through several stages of the construction. First, let's define a pre-sheaf on X, which takes such an open set U and sends it to, well, we can't really evaluate this sheaf F on the image, but we can evaluate it on open subsets containing the image. So here, first we take the set of all pairs V phi, where V is inside Y an open subset, which contains this F of U, and phi is a section of F on V. And then we divide out by one of these equivalence relations. So somehow if you have two such things, so this would be a V prime, some other set, then we say that these are equivalent if you find an even smaller set W containing F of U, so it must contain this red part, and sitting inside this intersection, such that if you restrict the two sections on the two different blue sets to the smaller set W, then they are the same. So in other words, we just take again some limit like this of such open sets and sections very similar to things which we have seen, for example, when we define this dog. And then you verify this is a pre-sheaf on X, and then you get a sheaf just by taking the sheafification. So this is always necessary in these contexts. So we did get ourselves a sheaf, which we now denote by F inverse of F, not F star, but F inverse for now. Now, one thing you can you can also check is that the stalks agree. So somehow if you have a point P here, then the stalk of this inverse image sheaf at P is the same as the stalk of the sheaf at the image point f of P. And the proof there just uses that, well, these stalks were also defined as being such equivalence classes of open subsets and sections. And then you just basically see that the two definitions agree. So we'll not go through this in detail. One problem is, so we wanted to define this pullback, which should be a module of sheaves on X. And the issue is that this F inverse of F is not an OX module. So it's not so clear how you would multiply by a function on U, because all the elements here are kind of sections on the other side. It is true that it is an F inverse of OY module. So somehow you can do the same inverse image on OY, then you get sections or regular functions on these open sets V. And then if you have like one section of F on some open set, and you have a function on some open set V, then you can multiply them and then you get a new section. And so this defines an F inverse OY module structure on F inverse of F. So you should just write this down for yourself, maybe an example to convince yourself that this works. So we didn't quite get where we wanted, but we're already kind of well underway. This F inverse of OY has the additional nice property that it is a sheaf of rings on X, because, well, OY is a sheaf of rings, and so you know how to multiply those sections. And so you also know how to multiply these sections here. And you get a homomorphism of sheaf of rings from F inverse of OY to OX. And there the idea is, if you have, let's say, some V and some regular function on V in here, this is a section of this F inverse of OY. How do you get a function on U? Well, you just take this function here and pull it back. This gives you a function on U. So basically, this map here from F inverse of OY to OX, this is an equivalent way to package this data of the morphism, right? In the data of a morphism of schemes, you do need to specify these pullbacks, and you can equivalently specify them like this. And then we have all the ingredients assembled. So we have this thing here, which is a module over this sheaf of rings. And on the other hand, we have a map, this pullback map from here to there. And so these two are both sheaves of modules over this sheaf of rings, and then you can take the tensor product. And then this is the general definition of this pullback. Now, this sounds very complicated, this entire construction. I mean, we have this pre-sheaf, we sheafify, and then we see these things via pullback, and then we take the tensor product, which also involves sheafification again. So I agree, this is a complicated construction. The good thing is, as we're going to see in a second, we basically never need to calculate all these sheafifications and so on. We just need to check now. So we define things two different ways, right? We started with this very simple construction, just on the module level. And then this was this arbitrary construction. We now verify that these give the same answer. And once we have done this, we can always just use the simpler construction to check things on open covers. Okay, so some observations. So first of all, this F pullback now is indeed an OX module. And this works very similar to the case A that we saw, namely if phi is a section of OX, then, well, you have this tensor product. You want to now see what does it mean to multiply an element here or a section here by phi. Well, you just take, you can take the identity tensor, the multiplication of phi on OX, itself. This gives you a map here, and this is exactly the map that you want for multiplying by phi. So this is very similar to how this here becomes an R module. You just multiply in the second part of the tensor product. And then the important compatibility is that if X and Y are affine, then you actually recover this construction in part A. And we verify this by looking exactly what the stalks do. So if X is spec R, Y is spec S, these are both affine, and F on spec S, it comes from this S module M. This is the situation of part A. Then we just try to see what does this construction here do? What does this F pullback of F do? Well, by definition, or somehow we have seen that the stalk of a tensor product is just obtained by the tensor products of the stalk. So somehow we take the stalk here, stalk here, stalk here. This is just some property of tensor products. And then we mentioned the stalk of this inverse image sheaf of F at P is just the same as the stalk of F at this image point. And similarly, if you apply the same thing here, we just see this stalk here is the stalk of OY at the point FP. And then finally, this thing we don't need to change. It's already nice. And then now this was a fully general. This works always. We didn't use that these are affine so far. But now we can use all this information, namely, for example, F is associated to this module M. And so its stalk at the point here is exactly just a localization of M at this prime ideal. Similarly here, so this is just the localization of S at this prime ideal. And then finally, this OXP, I mean, X is spec R, so this is the localization of R at the prime ideal P. So this uses that we can calculate stalks of these tilde sheaves as just the localizations of the corresponding module. And now this, there's just a kind of commutative algebra lemma that tensor products commute with localization in this way that this is just a localization of this tensor product here at this point. And now we are on a good track because we defined the in A, we defined the pullback as being the sheaf associated to this module here. And now we already verified that the stalks agree. And so the next step is always we construct a morphism of sheaves. This is now not so hard because from here to there, if you have a section, this is just a compatible collection of elements in the stalks. And so you can just take its values at the various stalks here and then see by this isomorphism they live in this localization, which is just the definition of how you can create a section of this here, right? A section of this tilde sheaf on U is just a collection of elements in the stalks of this module, or in the localizations of this module here. And so here is where we somehow in this interpretation use this collection of isomorphisms. And then this psi is the morphism of OX modules. It's compatible with multiplication, and it is also an isomorphism of stalks, basically because the stalk here is this localization, and we have seen that this localization is exactly the stalk of this tilde module. And so everything was an isomorphism. Then, as I said, so somehow this construction in B, that's a complicated construction, no doubt about it. But you basically never have to actually do that. What you just do is you use B to give you an argument that this is a well-defined OX module, and it is basically uniquely determined by knowing it on this cover. So for any and on the overlaps and so on. And so for any local computations, you can always just use this part A, and then you really just have to take the module, take the tensor product. So so this is this operation of pullback, and this is actually a very useful operation, as we're going to see in some applications in the last videos of the lecture.